Hi, I'm Irina Dudina, and today I'm going to be talking about static analysis for porting code to CHERI. So one of the goals of CHERI is to make it possible to just take existing C++ code and basically recompile it to CHERI so that it could benefit from the hardware protection that CHERI offers without applying much effort from porting. So in general, adaptation of contemporary C++ code to CHERI is quite straightforward and requires very few changes to the source code. And many issues are detected and actually well explained by the compiler, but still there are certain issues that cannot be detected by the compiler and they only surface at runtime during testing or using a project. So it would be nice to have a separate static analysis tool that could employ deeper and therefore more time-consuming analysis than a compiler can afford, and potentially having lower true positive rate than a compiler warnings are obliged to have. And so therefore having a better coverage and detect more portability issues. One other not obvious benefit of this comes from the fact that sometimes developers, when fixing compiler warnings, tend to just come up with the quickest, easiest fix just to silence the compiler, and that doesn't necessarily mean fixing the original issues. While static analysis is not as easily buffled, but just extra cost, for example, so it could also detect incorrect fixes of portability compiler warnings. So the most classical application of static analysis is to detect bugs in programs like buffer overflows, use after free, and so on. But that's not, I just want to emphasize that's not what we're going to do in this work. We're going to focus on portability issues detection instead. So we're going to look for code that works fine on the architecture that it was written for originally, but will not work on other architecture, for example, on CHERI. Like in this code, for example, we are passing an address of an unsigned long variable to a function, then we'll write a void star value to it. As long as unsigned long and void star have the same argument, this will work fine. But on CHERI, this is no longer true, so this code will not work on CHERI. And all my examples, or most of my examples, come from real code, so you will have references here. Another potential application of static analysis is program understanding. For example, collecting certain code metrics that will help you understand something about your program, and we'll discuss how that can help with porting if we have time. So our work is based on Clang Static Analyzer. Is a tool that is technically a part of Clang project. It has two analysis levels. So first of all, it has symbolic execution engine that is used for path-sensitive analysis. And it's interprocedural within one translation unit. And it also has IST matchers to detect quite simple problems like this. For example, again, when we have a call to calloc and we have size of expression as an argument, and underlying type of size of doesn't match the type of the returning pointer. So this is an issue. And again, while if these two types have the same size, it's fine, but that's not true on CHERI. So this is a portability issue that is detected by IST matcher. And Clang Static Analyzer can also be extended with custom checkers, and that's what we do for CHERI. So you've already seen this picture today. This is document C++ programming guide that's pre-existing to my work, or that has a comprehensive discussion of compatibility issues that may arise when you port code to CHERI. We just mentioned a few that is relevant to next slides. So first of all, capability size, so pointer size and alignment is increased, and this can be unexpected by some code. Also, you need to be very careful when copying or modifying capabilities because you need to preserve tag. That's, Vadim explained this previously. And also a lot of issues arise from storing pointers as integers, for example, in PGRT type. So what we had to do to address these issues in Static Analyzer. So this work is based on a CHERI LLVM, or rather Umbrella LLVM project that has, it's an LLVM compiler infrastructure with CHERI support. So we needed to make some small fixes to static analyzer for it to accept CHERI as a target as well. And we also need to extend support for lock as int. This is symbolic values in const static analyzer that appears when you store pointers as integers. So as I said, this is like source of common problems. So we need to be able to reason about this. So we had to extend support for this type and for arithmetic on this type. And we also added a capability tag to reason about whether this particular pointer stored as integer is actually a valid capability or not. So we also implemented 4 specific checkers, 3 symbolic execution and 1 IST checker that I'm going to talk about later. And we also found that at least 3 existing upstream checkers in client static analyzer are especially important when we're talking about CHERI. For example, the code that I showed you before with Sizov and calloc is from upstream checker. So I think one of the most useful and interesting checkers that we developed is a point alignment checker. Is intended to detect pointer casts that increase alignment. So it detects casts of underlined values to types with stricter alignment. Like, for example, in this code, we have array that is 1 byte aligned, and it is accessed as with 32-bit access. So this is a potential misaligned access. This is an issue on conventional architectures as well. It can result in a fault, affect atomicity or performance. But issues often persist in code and are not detected. First of all, that because they cannot just manifest. This pointer can actually always be aligned due to several reasons. First of all, certain ABI guarantees can make sure that this is always aligned. And of course, when you move to another architecture, you no longer have these guarantees, and this will be a problem. Then you may have some fragile properties of a current data layout. For example, you can have a field that has a certain offset from the beginning of the structure, and the whole structure might be aligned, and the offset might be nice. So your field will always be properly aligned, but this is quite a fragile property because just adding extra field to the structure will ruin this. Or a compiler may just decide to always put it on the aligned address for other reasons. Or your pointer may be misaligned, but the ill effects from that on a conventional architecture may be so subtle that you never notice and no one cares, basically. And this is no longer true for CHERI capabilities, so we have some CHERI-specific issues. First of all, alignment of pointers increased to 16, which is, well, a lot and not expected by many legacy code. Second, unaligned load or store of a capability will generate a runtime hardware exception, so this is not acceptable. And another thing that is, I think, quite unique to CHERI is that you're not allowed to store capabilities at underlined address, even temporarily. So you cannot copy it to unaligned address, then it will lose the tag at this point. And if you then copy it back to some aligned address, you will not get the tag back. So this is something like new for CHERI, and you will discover this later when you try to access this capability because you will be referencing untagged capability. So, and it's quite hard to debug this because you need to track where did the capability lose its tag. So to be able to detect that, we needed to implement pointer tracking of pointer and integer alignment as traits of symbolic values. And we also tracking memory regions that can potentially or will for sure contain capabilities because they were allocated for capabilities or because some capabilities were potentially copied to this memory region or using other heuristics. So that is for detecting memory copying capabilities to misaligned addresses. So this is one of the warnings that we got. So we have a structure that contains capabilities, and we're trying to allocate memory for it. So the address must be aligned. So we're using this function for allocating memory, and it actually assigns to this pointer, assigns an address of a field that has no explicit alignment requirement. So this code actually crashes on Morello, and yeah, it's not obvious. So it crashes when you're trying to use this memory, so it's not very obvious to fix this to immediately understand what's going on. So this is detected by static analyzer. So another checker that we have, it doesn't have a lot of true positives, and it was not easy to implement, but yeah, still. So it detects memory copies that may potentially copy capabilities, but they don't use, they copy memory in smaller chunks so that you will not copy capability as a whole, and therefore you will lose the tag. So for that, we need to track memory regions that potentially contain capabilities, check that the copy is not too small, so we can actually copy a capability, is not unaligned, so indeed this could be a capability copy, and then the chunks that we are copying with are small. So another checker is about storing pointers as integers and in point t. So it has already been explained today twice, I think, that when you add two in pointer t's, compiler has to derive provenance from one of the arguments, and it's not obvious which side to use. So compiler will give you a warning for this, but with static analyzer we can actually track provenance and tell you, okay, here you have provenance from right-hand side, and in some other case, provenance from left-hand side, and help you fix this warning. So we have certain warning messages depending on what exactly the case we are looking at. And surprisingly, the most useful warning is we figure out that as a result of such binary operation, we got a capability that is untagged, that is not derived, and then we use this capability as a pointer, so we cast this back from in pointer t to pointer type. So this warning gave us the most of useful warnings, really true positives. And the last one, this is a very simple warning that is just inspired by some code in SQLite, where you trying to check size of pointer, you consider different cases and fail to consider a case of 16 bytes pointer. So this is a very simple IST checker. So these are results. I checked this on selection of CHERI BSD ports. So first of all, we can notice that analysis takes about 4 or 5 times longer than the compilation, which is, I guess, acceptable. And so the most useful warnings is pointer alignment warnings, and this checker is still under active development. I still have more ideas how to extend it and how to get more warnings. So capability copy detector is not very useful. Most of those are actually false positives. And as I said, from provenance source detector, the most helpful one was this, when we have actually an invalid capability that we are trying to use as pointer. So as a result, we have CHERI support for crank static analyzer, 4 extra CHERI-specific checkers. I submitted it as a CHERI BSD port, the static analysis tool, as a separate tool. I had to fix built-in deception utilities can be able to work with CHERI BSD. I checked over 300 CHERI BSD ports, and for those that were marked as important ports, I submitted fixes for issues that I found. Yeah, so we have more ideas of what could be done. We have more checker ideas that could still be implemented, and As I said, like a program understanding approach, like gathering some metrics about code, could potentially help us estimate porting effort before we start even doing porting. So this is another way of approaching this. Yeah, that's it for me for today. Thank you.
Thank you very much. Very interesting and useful work. Now, do we have any questions? Yes.
So it looks like these changes that you've based on the CHERI Clang infrastructure could be kind of useful more generally, right? There's only a few of them that are sort of capability specific, like they're revealed by capabilities, but in a sense they're bad code in general.
You mean like issues that we found, like this, for example?
Yeah, for example.
Yeah, well, that's yeah. Usually, if the code is very like conforming to C standard, that it should be fine, and only like doing things that are a bit dodgy usually raise issues.
This code can be wrong on x86. This code can also be wrong on x86 because the behavior of atomics depends on alignment, and so putting something at poor alignment could cause atomics to silently fail on some microarchitectures. So misalignment is very visible with CHERI, but it isn't great on other architectures either. So I think it's an interesting point. But I think maybe more to the point, if you made this work with regular Clang LLVM, you could get it deployed to open source projects and warnings generated so the code gradually converges on CHERI happiness in the absence of people having Morello boxes and CHERI systems. So, if these were in baseline Clang LLVM and it's whining away about these habits, then our future gets better. Not this week, but in 3 years' time, it'll be much better.
Yeah, so maybe that was kind of the second part of my questions, which is how much do the implementation of your analyses depend on the capability specific bits? Like, could you backport it to mainline Clang?
Certain things like extended support for localizing can definitely be backported, upstreamed, you mean?
Yeah.
Yeah. So there are changes to Clang that can be upstream to LLVM, and there are changes to code, like for this, for example, that could improve just the code quality. Yeah, but we need them to get accepted to Cherokee deports first.
Jeremy.
Thanks for your work. It's really nice, and we've used it in our group, so much appreciated. Do you have any feeling for which of these analyses are most valued by the developer community? That one, right? Okay.
If the developer community is mostly me.
Okay.
But I think we have found it interesting as, we've been pushing CHERI out to industrial people to try. It's amazing how many people say how useful it's been just as part of their standard regression test, because it finds so many bugs. In fact, the one that shocked me is when AdaCore came back, who write, high integrity software, and they'd found some bugs in their code, which is kind of horrifying because they do things like, air traffic control systems and stuff like that.
I was going to ask about the interaction with optimizations. So, I spotted that one of the ones there was the memcopy one, where tag stripping happens. But I guess there are LLVM and other compiler optimizations that look at that and say, oh, it's a memcopy. I'll replace it with memcopy. And our memcopy would replace that. And that is a semantic change, which is confusing for developers. But I guess, are there other aspects of this where interaction with optimization level or specific optimizations actually changes the semantics in a visible way for the programmer that are interesting from this perspective?
Yeah, so from a static analysis perspective, we can analyze code before optimization happens, so we don't really see them. And sometimes we even try to, if we if we analyzing, for example, a beat code, like a more low-level implementation, we want to get rid of as many optimization as possible, and it's still hard to do. But it's there is an issue, but I think we were mostly looking at source code, and it's more for developers to, even if it works, it may be worth fixing because it's sloppy, dodgy, unclear.
I suppose another way of looking at this is, if we know that there are certain things that the compiler will do during its optimization path, which are probably not what the programmer wanted, those particular patterns could be identified during static analysis,
Yeah, I think, yeah.
which could be interesting. Very good. Oh, Jessica.
So you had a slide at the end with the various stats on a number of issues you found of various kinds. Do you have any sort of either hand wavy stats or concrete stats on what the distribution of this is across ports? Like, is it very clustered amongst a few ports, or is it sort of relatively evenly distributed across all of them?
It is clustered. So if we have, for example, issues with in-pointer T, it will be like 50 issues from that particular project and 0 from all others, because if you use in-pointer T, you will have them. If you don't, you will not have them. Yeah, so those are like from few ports, actually, we got it. That's not very true for the first point alignment checker. Yeah, so this is more evenly distributed.
Yeah, so I guess it'd be interesting to see an analysis for the different kinds, you know, what kinds of code is actually doing those kinds of things to better inform that.
Yeah, that's why I said that, like, program understanding, perspective gathering metrics about code could potentially give us some insights on, oh, this project will be easy to port, or like, yeah.
Right, let's just take one last question right at the middle at the back.
More out of curiosity, but is it conceptually possible to extend this to check for arbitrary undefined behavior with respect to certain variants of the C standard, and like how much more would you get, or is that just too broad of a class of patterns?
So as I said in the beginning, so initially static analysis is used for bug detection, so basically for detecting UVs, all kinds of UV, and those checkers are already in the upstream Clang static analysis. So you will find your buffer overflow checker there, your use after free checker. So this is kind of an upstream work, and our work is a little bit more focused.
Okay, I think we'd better draw that to the close. Thank you very much again.